Class D amplifier most complete tutorial for DIA, audience designers, based on International Rectifier Designing Practices High Performance Class D audio amplifier. In this tutorial, we will cover most critical Class D design aspects to be able to distinguish between good Class D amplifier designs and bad ones. Based on this knowledge, you will be able to understand why one eBay Class D amplifier model sounds great and others don't. This tutorial is based on largest chip manufacturer companies' publicly available application notes and reference design documents. Most of good eBay Class D amplifier boards are simplified large manufacturer reference designs. Special thank you to International Rectifier, Infineon, and Texas Instruments engineers for well-structured and most completed set of documents. For those listeners who have an electronic engineering background and willingness to study more, I added links to source documents at the end of this tutorial. Content. This tutorial consists of 6 parts. Altogether, there are 30 minutes of pure knowledge in compact, easy-to-understand format. Part 1. Overview. Part 2. Digital audio MOSFETs, where we answer to question why we need specialized transistors to build good quality Class D amplifier and analyze most popular transistor samples. Part 3. Output filter importance in Class D amplifier designs, inductors. Part 4. Output filter importance in Class D amplifier design, capacitors. Part 5. Digital audio gate drivers. In this chapter we will analyze popular gate drivers functionality. Part 6. Things to know designing PCB. In this chapter we will analyze PCB layout aspects and how to minimize noise in Class D amplifier designs. Today Class D amplifiers overcome traditional Class AB and Class A amplifiers in all aspects: size, power, efficiency, and what is most important, in sound quality. There are new companies stepping in a market with outstanding designs, where I would like specially mention Danish company Ice Power and Netherlands company Hypex, who made really great OEM models for professional and DIY markets. Traditional Class AB amplifier. Let's take a brief look on a proper Class AB amplifier design, what dominated in audiophile solutions for many decades. Class AB amplifier uses linear regulating transistor to modulate output voltage. Today we can build outstanding quality Class AB amplifier, but due to the low efficiency they require large heatsinks and active cooling solutions, what in most cases are unwanted noise source. Designs above 100 watts are expensive. Most reasonable priced consumer AB amplifier devices have power ratings from 70 to 130 RMS power. Amplifier classes and efficiency. With growing electronic market, efficiency become a more and more critical aspect of green energy concept. Let us take a look to audio amplifier types and efficiency. Class A amplifier can be made very linear, but with limited efficiency of 25 to 50%. The most popular version of audio amplifier AB can achieve 50 to 65% efficiency. Class D amplifier can achieve efficiency above 90%. And today this is the fastest growing audio amplifier segment. Class D amplifier. Class D amplifier employs MOSFET, which are either on or off state. Therefore, ideally 100% efficiency can be achieved. Pulse width modulation technique is used to express analog audio signal with on-off state in output devices. A loss in the switching device caused by finite transition speed, on-state resistance, and gate charge. So, how does Class D amplifier work? A Class D amplifier works in a very much the same way as a pulse width modulated power supply. Let's start with the assumption the input signal is standard audio line level signal. This audio line level signal is sinusoidal with a frequency range from 20 to 20 kHz, typically. This signal is compared with a high frequency triangle or sawtooth waveform to create the pulse width modulated signal as seen in the figure below. This pulse width modulated signal is then used to drive the power stage, creating the amplified digital signal, and finally a low-pass filter is applied to the signal to filter out the pulse width modulated carrier frequency and retrieve the sinusoidal audio signal, also seen in the figure. Major causes of imperfection. An ideal Class D amplifying stage has no distortions and no noise generation in the audible band, along with provided 100% efficiency. However, as shown in the figure, practical Class D amplifiers have imperfections that generate distortions and noise. The imperfections are caused by distorted switching waveform being generated by the Class D stage. The causes are nonlinearity in a pulse-width modulate PWM signal from modulator to switching stage due to the limited resolution and/or jitter in the timing. Timing errors added by the gate drivers, such as a dead time. Unwanted characteristics in a switching device, such as a finite on resistance, finite switching speed, and body diode stray. Parasitic components that causes ringing and transit edges. Power supply voltage fluctuation due to its finite output impedance and reactive power flowing through the DC bus. Non-linearity in an output filter. In general, switching timing error in a gate signal is a primary cause of non-linearity. The timing error due to the dead time in particular has the most significant contribution of non-linearity in a Class D stage. A small amount of the dead time, in tens of nanoseconds, can easily generate more than 1% of THD or total harmonic distortions. Accurate switching timing is always a primary concern. Total harmonic distortions and dead time. Class D amplifiers are based on switching technology where two MOSFETs are working in cycles. Dead time is a blanking period inserted between either high side turn off and low side turn on, or low side turn off and high side turn on. Its purpose is to prevent shoot-through or rush of current through both MOSFETs. Long dead time gives more safety, but rising total harmonic distortions. In modern designs, gate drive chipsets is responsible for minimum safe dead time insertion, and together with latest MOSFETs can provide total harmonic distortions below 0.003%. In the past, it was not possible due to the slow MOSFETs, what require long dead time and as a result total harmonic distortions. Probably this is one of the reasons why it took so long time to overcome classical AP solutions. New generation of gallium nitride transistors will be able to switch at very high speed and operate with negligible dead time values. Another marked cause of degradation in Class D amplifier is a bus pumping, which can be seen when half-bridge topology is powered in a low-frequency output to the load. Always keep in mind that the gain of Class D amplifier stage is directly proportional to the bus voltage. Therefore, bus fluctuations create distortions. Since the energy flowing in the Class D switching stage is bidirectional, there is a period where the Class D amplifier feeds energy back to power supply. The majority of energy flowing back to the supply is the energy stored in the inductor of the output low-pass filter. Usually, the power supply has no way to absorb the energy coming back from the load. Consequently, the bus voltage is pumped up, creating the bus voltage fluctuations. Bus pumping does not occur in full bridge topologies, because energy kicked back to the power supply from one side of the switching leg will be consumed in the other side of switching leg. In single-ended solutions, you need large power supply capacitors to eliminate bus pumping effect. Electromagnetic interference in Class D amplifier design. Electromagnetic interference in Class D amplifier design is troublesome like in other switching applications. One of the major sources of electromagnetic interference comes from the reverse recovery charge of the MOSFET body diode, flowing from the top rail to the bottom, similar to the shoot-through current. During the dead time inserted to prevent shoot-through current, the inductor current in the output low-pass filter turns on the body diode. In the next phase, when the other side of the MOSFET starts to turn on, at the end of the dead time, body diode stays in a conducting state unless the stored minority carrier is fully discharged. This reverse recovery current tends to have the sharp spiky shape and leads to unwanted ringing from stray inductance in PCB traces and the package. Therefore, printed circuit board layout is critical for both ruggedness of the design and reduction of electromagnetic interference. An important thing to remember from the slide is that printed circuit board should be designed with knowledge of all mentioned above. Historically, AB Class D amplifier designers don't have this knowledge and should learn from the colleagues dealing with the switching mode solutions. And the three major difficulties in a Class D design are PCB layout design, dead time generation, and overload protection. In the next part, Part 2, we will discuss Digital Audio MOSFET. Part 2, Digital Audio MOSFET. To build high-performance Class D amplifier, we need specialized MOSFET transistors with high switching speed. Key factors to achieve high performance level in amplifier are the switches in a power bridge circuit. Power losses, delay time, and voltage and current transit spikes should be minimized as much as possible in these switches, in order to improve amplifier performance. Therefore, switches with low voltage drop, fast on and off switching times, and low parasitic inductance are needed in this amplifier. Direct FET technology. Drain source LEDs and wire bonds contribute to both package resistance and inductance. Most of the heat transferred through the LEDs to PCB. So, how can we eliminate those shortfalls? Remove wire bonds from the package and replace with a large area solder contacts. Reduce package inductance and resistance. Copper can be enabled dual-side cooling. For example, new IRF6665 package transistors can operate at 100 watt amplifier without a heatsink at 8 ohm load. Advantages of direct FET. Reduce ringing. Inductance-related ringing reduced compared to SO8 package. Look at example below for direct FET and SO8 switching 30 amps at 500 kHz. Silicon of the near identical active area, rest of parameters are equal. Efficiency data. Efficiency close to 95% at the typical application of ± 35 volts and switching frequencies 395 kHz for standard 1 kHz input signal measured at 4 ohms and at 8 ohm operation. Total harmonic plus noise data. Let us look to total harmonic plus noise performance at the same test conditions. For 1/8 load we have unbelievable linearity values at 0.0057% at 4 ohms and 0.0031 at 8 ohm load. Let us remember that it is scientifically proven that human can distinguish total harmonic distortions below 0.1% value at any test conditions. Drain to source voltage switching waveforms. Direct FET package shows cleanest and fastest, approximately 3 times faster switching waveforms than amplifiers with a TO220 package. Half-bridge full pack. This digital audio MOSFET half-bridge is specially designed for Class D amplifier applications. It consists of 2 power MOSFET switches connected in a half-bridge configuration. The latest process is used to achieve lower on resistance per silicon area. Furthermore, gate charge, body diode reverse recovery, and internal gate resistance are optimized to improve key Class D audio amplifier performance factors such as efficiency, total harmonic distortions, and electromagnetic interference. These combine to make this half-bridge a high-efficiency, robust, and reliable device for Class D audio amplifier applications. Half-bridge full pack features. Integrate half-bridge package. Reduce the part count by half, reduce package inductance, improve electromagnetic interference performance, facilitate better PCB layout, enable single layout printed circuit board, better dead time control, LED-free package of course. There is well-documented international rectifier reference design ERODAM7S based on half-bridge package and IRS 2092 integrated Class D audio driver chipset with PWM modulator. So far, it is one of the most successful DI available design providing true audiophile sound performance when the good power supply has been used. And summary. Direct FET is the next step quality in Class D audio amplifier design. Evaluation of IRF6665 in Class D audio amplifier demonstrated improved efficiency, total harmonic distortion, and electromagnetic interference. Utilizing direct FET technology reduced electromagnetic interference comparing to TO220 packages. Thermal evaluation demonstrated that IRF6665 can deliver up to 100 watts per channel into 8 ohm with no heatsink. Half-bridge full pack features make the device an excellent option for a Class D audio amplifier applications. Integrated half-bridge packages reducing part count by half. Low package inductance improve electromagnetic performance. Digital audio MOSFET is a right switch for a Class D audio amplifier. In next part 3, we will discuss output filter importance in Class D amplifier design focusing to inductor. Part 3. Output filter importance in Class D amplifier designs, inductor. High-power Class D amplifier needs output filter to separate high-frequency carrier signal from the audio signal. In real life, this filter plays a significant role with high impact to total harmonic distortion and frequency characteristics. In this chapter, we will analyze the filter types and components to meet true audiophile requirements. Output LC filter frequency response properties. The frequency response of the second-order Class D LC output filter is critical when selecting the component values for the inductor and capacitor. The LC filter response also varies with the speaker load impedance. The load impedance determines the damping ratio of the output LC filter and is classified as overdamped, critically damped, and underdamped. It is also important to understand the speaker load impedance variations for the applications and select the LC values that suit the expected load variation. Ideally, the LC filter values is selected for the critically damped, flat passband and phase response. Two considerations when selecting components for a second-order low-pass filter is the cutoff frequency and Q factor or damping ratio. Trade-off 2. Inductor and distortions. The quality of audio inductor is crucial to achieving not only the target audio performance but also efficiency. Various inductors have a different total harmonic distortions, so you can build your design using the best components in the world and destroy amplifier performance just selecting bad output inductor. Inductance change with the load current, which causes distortions. It should be considered in your design. Selected inductor should have stable parameters across all possible current scenarios. Core saturation increase inductor ripple significantly that can trigger overcurrent protection. Frequency response example. Let us take one real-life example for bridged amplifier solution using correctly calculated filter values with L value of 10 microhenries, capacitor 0.68 microfarads, and Q factor of 0.707 or critically damped. From characteristics you can see that this filter has been optimized for 4 ohm load, where amplitude frequency characteristics are perfect in all frequency range from 20 Hz to 20 kHz. For other loads, you can see 3 dB fluctuations at 20 kHz. In best design, speaking may be optimized at within 0.25 dB range for 4 to 8 ohm load applications. LC Filter Quick Selection Guide. Look at BTL application where filter optimum calculation results using standard components. Best result what you can achieve is 0.05 dB for a fixed load scenario. It is far below human capability to distinguish the difference. It is scientifically proven that for a human hearing, amplitude frequency characteristics is perfectly flat when staying within 0.25 dB range. Inductor selection for high-performance Class D audio. An ideal inductor maintains a specific inductance value no matter what current passes through it. However, real-world inductor always have decreasing inductance with increasing current. At some point the current level saturates the inductor and the inductance falls off severely. This is often specified as a ESAT. Because inductor linearity is a function of current, inductor distortions is higher with lower impedance loads. Let us look at a real-life example from Texas Instruments. In Figure 21, the more linear inductors show improved midpoint, total harmonic distortion plus noise performance. With the worse inductors, both the 10 microhenry and 7 microhenry offers very high performance and nearly approaches the characteristic curve of an ideal amplifier. The distortion performance is noise limited nearly all the way to clipping as shown by the continuously decreasing slope of the total harmonic distortion plus noise plot. With a more linear inductor, we are able to see deeper into the noise floor of the amplifier before the harmonic content of the output signal begins to dominate the noise. Inductor selection for high-performance Class D audio. In the graph, Texas Instrument engineers presenting the number of inductors influencing harmonic distortions versus output power. You can see that only some of the presented good manufacturers' inductors are performing well. So, this selection is really critical. Good ones are expensive and costs up to $4 per piece, with board price impact of 10 to 20%. Therefore, many cheap eBay boards should be tested against inductor quality. Conclusion: inductors. From the results of the inductor study, it is clear that the inductor plays a significant role in the audio performance and total system power dispatch. Inductance value, direct current resistance, linearity, and core loss factor influence total system performance and must be considered based on the design goals of specific applications. In the next part 4, we will discuss output filter importance in Class D amplifier design, addressing capacitor selection. Part 4. Output filter importance in Class D amplifier design, capacitor. In this chapter we will discuss the importance of output filter capacitor. The capacitor in Class D output LC low-pass filter is critical to the frequency response of the amplifier. Capacitor ratings and specifications. What capacitor do we need for high-performance Class D amplifier? In fact, capacitor characteristics has been standardized. Today, I will not go through all definitions. This slide is for your reference. To read definitions, pause the video and read it through. There are following capacitor ratings and specifications: capacitance, maximum voltage or rated voltage, maximum temperature rise, equivalent series resistance, dispatch factor, dielectric material, and mounting type. Selecting a capacitor type. There are 3 large capacitor groups provided by manufacturers: metallized film, ceramic, and electrolytic. Only film and ceramic capacitors suit for amplifier output filter, where ceramic capacitors are considered only for a low power and high total harmonic distortion applications. Ceramic capacitor problem. Ceramic capacitors as a guideline. Ceramic capacitors reduce in the capacitance value by the same percentage of operating voltage to the rated voltage. For example, when 50 volts is applied for 100 volt rated capacitor, the capacitance decrease by about 50%. Capacitor type, tolerance comparison. Let's look at the table below. Capacitor tolerance determines how close we will be the theoretically calculated values, and the winner is film capacitor again. Dispatch factor, film capacitor is the best. Equivalent series resistance, film capacitor is the best. Choosing capacitor for low-pass filter. For audiophile applications with high amplifier output ratings above 100 watts, to achieve the highest sound quality, we should use non-winding structure metal film capacitors. Non-winding propellant dielectric type capacitor is on the top of the line. Costs. The best capacitor is coming with costs and size. Capacitor itself will cost more than $50, even at large volume purchases. Capacitor dimensions influencing printed circuit board size. When purchasing eBay Class D amplifier boards, inspect do they have a large dimension capacitor near to the inductor. Lack of such capacitor indicates that you are looking to budget design version using ceramic type of solution. Capacitors. Conclusion. Most high-power audio applications use either metallized film capacitors or ceramic capacitors. For best audio performance across temperature, voltage, current, and frequency, metallized film capacitors or similar are recommended over ceramic capacitors. Ceramic capacitors may be used in very size-constrained applications and should be tested thoroughly for reliability purposes, but audio performance may suffer. Part 5. Digital Audio Gate Driver. Good gate driver chipset simplifies Class D amplifier design a lot. In this tutorial, we will discuss latest generation gate drivers. IRS 2092 is most popular chipset in DIY and professional designs. The IRS 2092 is an integrated driver chipset featuring protected PWM switching for medium power, high performance Class D audio amplifiers up to 500 watt. Based upon a half-bridge topology, the new audio driver integrated chipset integrates 4 essential functions for Class D design implementation, including error amplifier, PWM comparator, gate driver, and robust protection circuits. As a result, this compact 16-pin chipset offers a high noise immunity, reduced start and stop click noise, and design scalability, with greatly reducing some of the most complicated and costly design tasks such as overload protection. Inside of high voltage gate driver IRS 2092. Key IRS 2092 features include analog PWM modulator with frequency up to 800 kHz, programmable bidirectional overcurrent protection with self-reset control, undervoltage lockout protection, and programmable preset dead time for improved total harmonic distortion performance. Erodump 7S. Erodump 7S is one of the most successful international rectifier reference designs using a single layer board. There is a lot of relatively good China-manufactured Class D amplifier designs targeting the DIY market with output power from 150 to 350 watts. But so far, original version is unbeatable when we're talking about power and quality performance. It is true audiophile grade unit for speaker systems with nominal power of 150 watts. Erodump 7S schematics. Erodump 7S is well documented, and you can find PDF reference design documents with simple search with right keyword. It is a very good document to educate yourself. There are PCB layout and detailed bill of materials available as well. You can study manufacturer's selected components and analyze them based on this tutorial acquired knowledge. But look at simplicity of design. I have tested number of units with a good power supplies. This amplifier outperforms most of the commercially manufactured units and stay in line with the most expensive ones when we are talking about the sound quality. In my channel I placed 2 DIY addressed videos with instructions on how to build such amplifier by yourself. Erodump 7S original and under license produced model. And the good thing is that you can purchase under license manufactured clone for price 3 times cheaper than original module. There you can see full Infineon driver lineup. The IRS-2052M digital audio driver is 2-channel version of IRS-2092, with additional features such as internal clock over temperature protection, temperature sensor inputs, and fault reporting outputs. Currently, it is one of the most completed Class D driver circuits, and I found them in many professional designs with power up to 500 watts. With bridged solutions, you can go beyond 500 watt limits. Connection diagram for 2-channel output is simple and takes small printed circuit board footprint with rich features. And features: 2-channel integrated analog input Class D audio amplifier driver, versatile protection control enabling latch, non-latched and host control edge shutdown functions, integrated clock oscillator, clipping detection, external thermal sensor input, on-chip thermal shutdown with warning, programmable overcurrent protection, programmable dead time generator, start and stop click noise reduction, undervoltage protection. And it is built for high noise immunity. Audio amplifier driver portfolio IRS-2452. IRS-2452AM is a targeting transformer-free distribution amplifier market where you need high voltage output working with a large number of speakers, with input resistance 20 ohms. The IRS-2452AM is 2-channel Class D audio amplifier driver rated at 400 volts, with integrated PWM modulator and overcurrent protection. Combined with the 4 external MOSFETs and passive components, the IRS-2452AM forms a high voltage 2-channel analog input Class D amplifier. The IRS-2452M is equipped with a startup click noise reduction to suppress unwanted audible noise during PWM startup and shutdown. Here you can see typical application circuit. 500 watts 2-channel constant voltage Class D audio amplifier using IRS-2452AM. In this slide you can see distribution amplifier reference design board and specifications. An amplifier can deliver 500 watts at 20 ohm load. Reference design is well documented. From manufacturer site you can download reference design document, bill of materials and PCB layout. Pay attention that for high current operation there are buffer stage between driver and MOSFET. And summary. Benefits using later generation gate drive chipsets. Any engineer could design audiophile Class D amplifier just following basic guidelines. Reduced amplifier price and improved quality. Shorter design time. Easy to make well-protected designs critical for professional market. 2-channel chipsets reduce amplifier size and are perfect for high-power budget solutions where quality is not a trade-off. In next chapter, part 6, we will discuss things to know designing printed circuit boards. Part 6. Things to know designing printed circuit board. In this chapter we will discuss things to know to minimize noise in your designs. Source of noise in Class D amplifier. There are two areas of noise source: switching noise and audio noise. Switching noise is generated by the output MOSFET switching in wide range of frequency spectrum above the audible range. The amount of switching noise depends on switching speed, size of the MOSFET, load current, PCB layout, location and quality of bypass capacitors. Audio noise. Audio noise is noise ingredient in audible frequency range in the speaker's output. Major causes of audio noise includes noise figures in the front-end error amplifier, jitter in switching time, radio frequency interference noise from switching noise injection, thermal noise from resistors, and hum noise from ground lobe. Noise reduction strategy. Minimize noise source in switching stage, maximize noise immunity in analog stage, minimize noise coupling from switching stage to analog stage. Minimizing noise sources. Self-commutation at idling, if ringing check shoot through, check dead time. Reverse recovery charge, QRR, caused hard switching that triggers resonance in STRI inductance. Slower switching helps to reduce QRI. STRI inductance is where excessive energy is stored. Look for optimum trace layout to minimize STRI inductance. And careful component selection is key to minimize STRI reactance. Reducing noise with RC snubber. RC voltage snubber is used to suppress voltage spikes in switching and power supply nodes. Resistor in RC snubber absorbs energy from reactance by damping resonance. To maximize effectiveness of snubber, resistance should be close to impedance of resonant element. Capacitance should be larger than resonant capacitor. Capacitance should be small enough not to cause too much dispatch in the resistor. Power dispatching from resistor could be calculated by formula below. Maximizing noise immunity. Place input radio frequency filter. Filter out high frequency noise and reduce node impedance at high frequencies. Put differential input radio frequency filter. Prevent RFI causing audio frequency interferences from switching rings. Feedback low pass filter. Weed out high frequency spectrum to avoid timing distortion in the error amplifier. And ground can be route of noise injection to error amplifiers as well. Often DI amplifier designs need input signal regulator, but be careful with that. Typical power amplifier input resistance is around 10 kΩ and contains noise suppression filter. It's meant to work with low impedance source at 50 to 150 ohms. If you put high impedance audio regulator, you will influence audio signal characteristics where high frequencies will be filtered out. Minimizing noise coupling. There are functional blocks that generate noise. There are functional blocks that are sensitive to noise. The PCB designer should identify them and find out the best combination of the placement based on these facts and mechanical and thermal requirements. Noise-sensitive functions. The audio input circuitry, the PWM control circuitry, noise-generating functions, the gate drive stage, the switching stage. Switching noise injection sample. In this sample you can see that even minor design simplification or mistakes can significantly influence audio performance. It may be one of the reasons why under license manufactured ERIOSAB 7S module performing better than simplified cheaper versions with similar architecture. Printed circuit board design tips. The first and most important step for printed circuit board designers is to group components dedicated to common purpose, such as the audio input circuitry, the pulse width modulator control circuitry, the gate drive stage, and the switching stage. By identifying which component belongs together, place the remaining circuitry by coupling them properly into open areas of the board. PCB layout example. Printed circuit board layout is equally important to component placement. PCB tracks are film-type conductors with resistance, inductance, and capacitance. For Class D amplifier design, we should take it into account. Things to consider. Separation between analog and switching section. Minimize trace impedance with the planes in the power section. No overlap between switching nodes and analog nodes. If you are there, then I assume that tutorial brought some value. In the digital world, we never know who will be our audience. Maybe you are interested in electronic design or just looking for compressed knowledge to make right purchasing decisions. In my next videos, I will review selected eBay amplifiers, measure performance and characteristics. Winners will go for DIY design samples. My focus will be to audiophile grade amplifiers in power range from 150 Watt to 600 watts. It will cover 90% audiophile real-life needs. For scenarios of 1000 watts and more, I would recommend professional designer products. Those are other class products with safety requirements and electromagnetic compatibility certifications considered. Before leaving this tutorial, look at the picture below. It is state-of-the-art ICE power amplifier design. This model incorporates a number of smart engineering solutions, has great sound, could work on 4 ohm load in bridged connections. The only thing to be missing is balanced inputs. Today, ICE Power 125 AS6 II is only professional grade module broadly available for DI market at reasonable price. What next? Gallium nitride transistor designs. Today we are moving from scientist labs to real-life applications. I have seen reference designs of 500 watt amplifiers with no heatsink and capable operate on 4 ohm. Unbelievable. Infineon and Texas Instruments has their first gallium nitride gate drivers and transistors available in the market. In the nearest future we can expect amazing power supply and amplifier designs. Don't expect them to be cheap, but they will be extremely compact and efficient. And at the end, there is the reference documents what I used to build this tutorial. With a simple search you can find them and drill down. They contain a lot of valuable information. Looking forward with the real-life board tests. If you gain some value from this tutorial, please put a like. Your likes are similar to an air bubble, giving chance this particular video to move from the deep information ocean to the surface, where other people can see it. It is important for me as well to find the right format for right audience.